See here. Today's topic is section 2.2 out of our notebook, where we analyze conditional statements. The big box at the top of your notes is for you to work these three problems, see what you remember about factoring. All right, so here are the answers. Number one is just simply a greatest common factor. Number two is the two binomials. And number three has two steps. First, factor out a three, then take it to the two binomials. All right, so we've come to the official part in the book where we talk about a conditional statement. We've already worked with them a little bit in our two-column proofs. They are simply statements that are written in if-then form. So a conditional statement is a logical statement that has two parts, a hypothesis and a conclusion. So the if part contains the hypothesis. All right. The then part contains the conclusion. All right, so go ahead and study the example from the smartboard. You don't need to write anything here, and then we'll jump back over to the notes here. Okay, so this is not written on your notes. I'm just showing it on the smartboard. So it says, study the example. What is the hypothesis and conclusion? If you study hard, then you will earn good grades. Okay, pretty basic, right? If you study hard is the hypothesis, then you will earn good grades is the conclusion. All right, example 2 here asks us to rewrite the statements below in conditional form. That means to put it in if-then form. So the first statement is all whales are mammals. So you can go ahead and pause if you want to and see if you can figure it out. This one actually is kind of tricky. So the trick with turning something into a conditional statement, and you'll have to do this a little bit on your assignment tonight, is sometimes you have to add words in there that add meaning for grammar purposes, but don't change the meaning of the statement that's in front of you. All right, so A says all whales are mammals. So we want to think about if, right? And then we need a then part. So sometimes the magic word that you add in there is it. That seems to work for a lot of them. If it is a whale, then it is a mammal. But for this one, I think that maybe I'm going to add the word animal. If an animal is a whale, then it is a mammal. Okay. Part B. This one's actually a little bit easier. 3 points on the same line are collinear. So how do we turn that into if and then? All right, so if, maybe think about it for a second, then tune back in if you want to pause it. If 3 points lie on the same line, then they are collinear. All right. So the word that I added in here is lie, or you could say if 3 points are on the same line. So yeah, sometimes you need to put in those meaningful words without changing the meaning of the actual statement. All right, the next thing that we are going to talk about is a negation. And a negation, I'm going to make this symbol big, has a little symbol that goes along with it. And it is that symbol right there. It's, I guess, it's called a tilde. Okay. If you are asked to write a negation, it means to negate the verb. All right. So sometimes people do creative things here and they'll say the sky is red. So we're supposed to negate. So we're supposed to do a negation on this. And people will say the sky is blue. But really what we want to think about is the verb here is the word is. And so we are going to negate that. The sky is not red. Okay. And then The second one down here, the sides are not congruent. So this one already is a negative verb, right? Are not. So if you negated it again, it would say the sides are not congruent, which basically means that the sides are congruent. Are congruent. All right. Okay. Let's see. On the back, we've talked about a converse. Um, and I'm going to put some kind of symbolic notation in here to help us remember these because these are all things that we do to sentences. Sometimes we add a negation, sometimes we add a converse and whatnot. And so they get kind of confusing and they get hard to remember. But if you remember the symbolism, then it'll be really easy to remember what to do. So the term, there is really no term in this first box. All we have is the original statement, but I am going to add this notation here. And let's see, I'm going to actually go here because I want to get a special symbol out of this, out of the equation editor. All right, so P, and then I'm going to grab the little arrow symbol, Q. All right, so P will represent the if part, and Q will represent the then part. All right, so whatever is in front of this little arrow is the if part, and whatever is after this little arrow ends up being the then part. So the original statement is just written in the if P, then Q form. All right, there is no definition to write in this box, but here's our original statement. It says, if you are a soccer player, then you are an athlete. And a lot of people, I think, would agree with that. Although I will say sometimes people, oh, I'll try to highlight it, try to go a little too deep into this, but it would make sense that if you are a soccer player, then you are also an athlete. All right, so the converse, which we have practiced before, is when you swap the if and the then part. Okay, so that's going to look like this. I'm going to take the if part and put it before the arrow, so the Q goes first. All right, and then we have the P. So what that means to do, oh, let's see. So maybe I should go up here and just kind of comment that the if you are a soccer player would be in the P position, right? Then you are an athlete is in the Q position. So we are going to just swap around the P and the Q. So it's going to say, if you are an athlete, then you are a soccer player. All right. And people typically feel that that is not a 100% true statement. So we would have to answer that one as false because if you are an athlete, I mean, maybe you're a skier, maybe you're a swimmer, maybe you're some other sport. You don't have to be a soccer player. Okay, and so let's see. Let's go back over here. We're kind of used to doing definition. We're kind of used to converses, so I didn't write the definition out, but it's when you switch the if and then meaning, or I'll just say switch the if and then parts. Okay, so the inverse is when you go back to the original statement. Let's see. And we negate the verbs. So, oh, let me move this guy over here. So here's the little symbolic for this one. It's if P, all right, arrow thing, then so if not P, then not Q. All right, so all we did was negate the original statement. Okay, so I'm gonna go back to my text box. Negate the original statement. Okay, so our original statement was if you are a soccer player, then you are an athlete. So we're going to negate those verbs and it will say if you are not a soccer player, then you are not an athlete. Okay. Let's see. So if you are not a soccer player, then you are not an athlete. Is that true or false? I don't know. A lot of people would view this as false. If you are not a soccer player, you might be some other player, in which case you could still be an athlete. All right. And then the contrapositive. The contrapositive is when we negate the converse. Maybe I'll write that first. Negate the converse. All right, so we have to do a converse of the original statement, and then we're going to negate it. Okay, so let me see. The little symbolic part here is going to be not Q. If not Q, then not P. Okay, so our statement, if we went back up to the converse, if you are an athlete, then you are a soccer player, would be if you are not an athlete, then you are not a soccer player. All right, and then we're supposed to assess a truth or a false statement about that. Let's see. So if you are not an athlete, then you are not a soccer player. And many people feel that that would be a true statement, right? If you are not an athlete, then you probably wouldn't be a soccer player. Okay, let's see. So definitions. So in geometry, we have three things. We have definitions, we have theorems, and we have postulates. Those are the three main components that go into a two-column proof. And I mean, we use them in other areas of geometry. They come up all year long, but the important thing to know about definitions is that a definition and its converse will always be true. A definition and its converse will always be true. Okay, so I'm going to just, you can pause and write that out if you need more time, but I'm going to give you an example down below. This is not actually on your notes. I'm just going down here. So we had a postulate that we were using in our two-column proofs that said if two angles are right, then they are congruent. So if you try to take a converse of that, it says this: if two angles are congruent, then they are right. So when you think about that, if two angles are congruent, then they are right. That is not true. I mean, it might be true, but that is not true 100% of the time. There's a lot of congruent angles that don't have to be right. So I'm putting a strike through on that. And that is why postulates are true the way that they are given to us, but we should never take converses of them. If the converse happens to be true for a postulate, then they actually will give you a second postulate that would be that converse. But the mark of a true definition is that its forward part will always be true and its converse part will also always be true. Okay, on to perpendicular lines. So perpendicular lines are just two lines that intersect at right angles. And the symbol that we use in geometry is this upside down capital T right there. So when you see that, that means perpendicular. I'll go ahead and write the definition. And then I also had drawn this little picture off camera so that you didn't have to watch me painfully try to write it. So you go ahead and copy that picture and we'll talk about perpendicular. All right, so two lines that intersect to form right angles or a right angle. All right, and I did not put this one in if then today. We'll save the if then for tomorrow because tomorrow we're going to be using it in our two-column proofs. Okay, and on the right-hand side, I have a picture and I did this off camera so that you wouldn't have to painfully watch me try to type all this out from the equation editor. But what I wanted to focus on was this statement right here. This is very important that you understand. What this means, when you see that upside down uppercase T there, that means that segment AB is perpendicular to CD. And the result of perpendicular segments will always be that you have at least one or more right angles in your diagram. So the right angle is clearly marked here where the box is. And so that's angle CEB. So we could say that angle CEB is right. And the next one is angle CEA. The one next to it, CEA, would also have to be a right angle because angle or line AB is a straight line, which means that this angle AEB, is 180 degrees. So if this much is 90, then the other side of it would also have to be 90. And likewise, I didn't type it out, but these two angles underneath here, DEB and DEA, would also have to be right angles. And we have a proof, or I think a definition coming up, or a theorem, that if you have one right angle, then you should have all four right angles. All right, and the last part on your notes is something that we don't really use, but it is kind of part of this book, or this section, called a biconditional statement. And that is something you can apply to definitions. So remember, the mark of a definition is that its frontward statement and its converse will always be true. And when that happens, we can write a biconditional statement. So it says, when a conditional statement and its converse are both true, we can write something in biconditional form. So we know that the definition of a right angle is, if an angle is right, then it's 90 degrees. And its converse is, if an angle is 90 degrees, then it's right. So that is a definition of a right angle. And so to convert it to biconditional form, we would say an angle is right if and only if it is 90 degrees. And I don't actually think we're going to be using that too much this year. Okay, that's it for the notes, guys. Thank you.